You would have heard of this functional programming paradigm, right? So LIST is where does it stand in this functional programming? So functional programming, what happens is that we basically consider functions are programs are completely built of functions. Okay, basically functions in the sense that you give the input and you get the output, and there is no side effect. Even the like opening a file, printing the output, all of this is not considered to be a, it's considered as a side effect. Okay, so somehow this functional programming, pure functional programmings, they don't have this, what do you call that? They call these as side effects. Okay, so side effects is something which doesn't help you to give an output. So functions are basically you give an input and you get an output. All right. So anything that doesn't do that, anything that is like printing to the screen or any side opening a file, writing to a file, all of these are considered as side effects, and they have a different way of dealing with these side effects. Okay, so they in pure functional programming language like Haskell and there are other things like Haskell. There they actually treat this these activities like printing to screen, other things that don't help you in the function output, they are considered to be as side effects, and they treat them differently. Okay, so we want so Lisp, where does Lisp stand in that? So is Lisp a purely functional programming language now? It's not a purely functional programming language, because the core idea of functional programming is that you should you shouldn't do anything extra thing. I mean, you shouldn't have these so-called destructive operations. Okay, there's some principles there. So for that, to understand why, where does Lisp stand in that, we can look at this example here. So in that, they give you, first of all, what you have to understand is that unlike in pure functional programming, so these pointers usually will not be there. Okay, they won't have something like pointers, or if it is there, even if they have pointers under the hood, they will abstract away that thing and they'll give you like functions which you can be guaranteed that there will not be any side effects in your in the data that you're manipulating. All right, but whereas here what is happening is so from a functional perspective, what does this so there is something called append. So first of all, we have not done the append thing, so we just saw that in the macro definition, which I mean, it's kind of used there, but we haven't seen it properly. So basically what it does is it takes two lists and appends them together. Okay, and in fact it can take an arbitrary number of lists. You can take any number of lists and it will just put one after another, they will put it in. It just combine the lists together to produce the output. Alright, but the issue with this append is that there is a shared structure. Okay, so when I do, let's say I've already defined a list, and I've defined another list called list2. Alright, now when I do append of, I'm doing this append and I'm setting it to another list. So we have done list before, right? So I'm just using a list to append to build another list. Okay, so this is the case here. But what happens here is, notice that the second list, you can just going back to the example, which is basically 3 and 4. Alright, and I'm setting this as 3 and 4. So this is my initial list. This was my second list. Alright, and when I do append, I am getting a third list called list. Now what happens here is that this internally it takes the cons, which is nil here, it takes it and it points it over here. Right, so that you get a shared structure in this list. So there are some the functions that you use might create this type of shared structure, and an example is append. Append actually creates for you a shared structure. Now this shared structure is fine until and unless you have something called so this actually breaks the functional programming paradigm. Okay, so you cannot see things as basically Lisp is not a purely functional programming language because you have these side effects. Okay, and in particular these destructive operations are what so-called destructive operations in functional programming paradigm we call something called destructive operations because you have the side effects will impact your will impact your data structure. It will impact your approach to programming. So anything that manipulates side effect in the functional programming paradigm is considered as destructive operations. Okay, but in that also there is since this predates the functional programming paradigm, the purely functional style of programming, you can't use those terms on this language. Okay, so but you have to keep in mind this thing. So this shared structure can cause some amount of issues in the uh, in the in this thing because see the list one points here, list two points here. Okay, and this append creates a new list. So that this example is makes it very clear. So I have created a new list from these two. Okay, now if that was all we had, that would have not been a problem. But we have something called setf. Okay, which I had told you earlier is a more general, a very general way of assigning things. It helps you to assign things and it creates a for side effect operations. This is a type of operation we can say. So it's a operation that is this side destructive operations in functional programming terms are of two types actually in this. One is for side effect, another is recycling operations. Okay, so for side effect is like it actually changed the structure. Suppose you had this. So what's happening with the recycling operations is that for the side effect operations. So with the shared structure, right? The issue is that you can actually do this something like char star list. What's happening here is you have something called setf, and setf actually allows you to set the elements of the list. Okay, so I'm going to do a cadr. All right, I'm going to say like 0, which is the example what I'm saying in the example, but I just mistyped it. So let's just see this. Okay, there should be a hyphen here. All right, so I'm going to set the list thing. If I see the value, it is now 30. Okay, so okay, that's the second element of the list. All right, I have reset it. Now what will happen is this will get reflected there, and the reason for that is simply that you have this shared structure. Okay, I hope the shared structure is clear. So when you modify this guy here, you're actually modifying that list because internally the list consists of when you did append, you actually create a shared structure, and the other way also is thing. I mean, basically it's the same thing. The last part is the same list. Okay, it's always the last part is being shared in the append operation. So if I say setf of caddr, let's put char of star list to list star. Okay, which is the first element. I'm putting it, let's say 100, right? And so I have this star list star. Okay, we have 100, but this will not change the list 1, which is the original thing. That doesn't change. But if I say setf caddr, CDDR is basically, let's see what CDDR is, just to verify. Star list. Okay, so that is 3, which is this element here. That was coming originally from list 2. Okay, so you see here, this was list 2. So this is the list 2, which was initially there, and which is now coming from here. So if I do a setf for that, if I say, let's say 1500. So first of all, my list has changed. So this is like, yeah, you can also set that particular position. Okay, so that is one thing you need to note. And also what you see is that due to the shared thing, you will have it would have reflected in the original list. So that's the concept of the shared structure. All right, so that you need to keep in mind. And that actually creates this thing. Now what happens here is there's something called reverse. Okay, Recycling is nothing but so that's an example of a side effect for side effect operation. Recycling operations are a bit different from for side effect. And again, this goes back to the fact that the motivation and the context is different in Lisp. Right? Lisp doesn't try to be a pure functional programming. You can do arbitrary stuff, and it's up to the programmer again. Okay, the programmer should know what he's doing, and basically it facilitates things for you. It doesn't come in the way of anything that you want to do. You have to have a kind of discipline and consistency with what you need to be clear with what you're doing. So that setup you have to be careful with this type of structures. All right, so structures that actually modify the list. So if you do see if I do reverse, it doesn't change anything. Okay, it doesn't change the list per se. Okay, but let me just try this end reverse. It's another type of reverse. Let's see what's happening here. Get it? So let me give another example. Let's just try it out with a simple thing. List star. Let's say 3, 5. Okay. So I have these first 5 odd numbers. I'm taking the list. If I say reverse star list star. Okay, and if I go back to the list, it doesn't change. Okay, but if I say end reverse, it actually changes the list itself. All right. The reason for this is that the point is that so it's not really the definition. The way it's defined is not that. The point about this this is actually to, so you can see that it has actually it has modified the original list. Okay, but the point here is the reason for that is the example he has given is basically suppose I want to do this. Okay, if I did this, what would have happened is basically this reverse creates a new copy. Okay, reverse is a kind of, you can say, a functional style of things where it creates new memory. Okay, so that it has to create a new memory thing. It has to allocate some new memory and return the result of that reversing that list operation. So it creates another copy, completely new copy of that original list. But this is fine, but what will happen here is, if you do something like after this, if your only reason for reversing is you don't care about the original list, okay, and you are actually doing this, then it's a waste of computation. Okay, because you have to allocate memory and you have to do some amount of extra work, bookkeeping and all that, to create another list. But then what you're doing, you are creating the list, you're setting it there. This then becomes a garbage thing. This original list becomes free and you can actually garbage collect it. All right. If you were creating a new list, it would have been fine. This would have made sense because you're doing some extra computation. You have to go back to the original motivation. And those days, the number of your thing was very less, right? You had less memory, less things. So you were not very interested in. You don't have the luxury for having some very neat things. If you were to write purely functional style, you would not be able to run many things. Okay, so the motivation was different in those days. So it was more of how fast you can compute and how you can scrunch up on space and I think on time. So here what's happening here is that if you were to allocate everything, it's a waste. If it's a new list, it's fine. It makes sense to use reverse. But if you're not interested in that, you just say end reverse, which is non-recycling. Okay, basically what it's saying is non-consing. Non-consing, the sense that you're not creating new conses. Okay, so that's the point here, which means that it's up to the implementer. You cannot depend that list will change for sure. That's not what you're saying. You're just saying do the most efficient way of computing it. All right. In our case, what happens is that it seems to be changing the data structure itself. Okay, but the best way to be sure, it's better to set f star list star and reverse end list. Okay, because there's no guarantee. that you will actually have the result of end reverse in list. It doesn't say that. Okay, so there's no guarantee in the non-recycling thing. But you can, if you want the functional version, you use the reverse. Okay, so there are many things like this in Lisp which are having this. If you end is for I think end reverse is like a, you can say, efficient implementation. In particular for end reverse, what it's doing is basically it's traversing the array. Let's say it's traversing the array. Okay, so let's go back to that example here. So it's traversing the array. It's taking this guy and it's taking this one's cons and it's putting it here. Of course, the first one will be nil, but you're taking this thing. You're storing this pointer. You're taking the next to next and you're pointing it back like this. Of course, you have to you have to do it efficiently. I mean, you have to remember there's some amount of bookkeeping involved. But what you're doing is basically you're making this nil. You're taking this guy and pointing to this. Then as you go along the array, and in one pass you can actually do it. Okay, you have to do some bookkeeping because you have to say take this guy. First you have to make it nil, and then you have to take this guy this and retain store that temporary variable and point this to thing. Then go there and then point this like that. So it will go. You can do it in one pass though. And then finally, when you reach the nil, you basically return that list. So this would be the most efficient way of implementing it. Obviously, a little bit of you need to take care of the data structure and variables, but you can actually do it in one pass. Okay, so that's exactly what that's mostly how it is implemented. But the thing is, there's no guarantee with the n reverse or other functions like nconc. Okay, so there is usually no guarantee, but some of them also have guarantee. So there is no so yeah, that's the situation there. There's some end reverse. Okay, end reverse means non-consing usually. When it starts with then, it's like non-consing. There's an nconc, the recycling version of append, and then you have end substitute. All right. So these options you have. So basically, it means that it's non-recycling. Okay, meaning that non-consing. Sorry, it's not recycling because it is it is not recreating for you a new thing. Okay, it's not it's just basically it's recycling things. What does it say? Recycling. Yeah, recycling in the sense non-consing. So if consing is considered to be a waste of space, it has to create new things. So you're not doing that. All right. So you're just reusing things. So you don't care about how it is implemented. Okay. So also we had a look at first and rest. There's also some list type operations and map car. I thought I'd just take it out. Okay. So if you have like hash port, yeah. So there's some few more list operations. We had earlier covered list operations, right? So we can look at so this to take care of the shared structure and recycling. Okay. So side effects in Lisp are actually there. So it's not like you don't have side effects. Setup you have to be really careful with because you should take care of the shared structure, and recycling operations is like for optimizing the side effects used for optimizing the operations. Okay, so that's how you have to take care of this these two aspects of Lisp. When you're dealing with Lisp, you have this side effects. And so some more list operations that we had was we can look at some list manipulation things, some things are really this map kind of thing. Since we have now done the functions, lambda expressions, higher order functions, map is actually a higher order function. Map and its related things. So map car is like it's like this. Okay, so you take as function as input. Again, you have a lambda expression, and you take this list. Okay, and then what it does is it actually takes a function and applies functions to each of those elements. All right, that's what it does. And then what you can do is you can do a reduce hash colon sum. All right. Sorry, sum is not existing here, so we have to define it as that, or we can just say plus, right? So I think this map reduce kind of thing this is pretty old stuff. Okay, in Lisp it's like that from a long time, but basically, so inside what you're doing in map is you're taking a function. Okay, so now that we have higher order functions, we have done some exercise on that, and you can revise it, but you can also do this. You can think of this. Okay, map family of map operations. Okay, so mapcar basically what it does is it applies to the yeah, this is how it works. Okay, yeah, so it's like it's just a map thing. So there's a difference between mapcar and map list, because yeah, so the theme over here in this map family of operations is we can look into this. I mean, it's not very important like to go to the specifics of it, but just remember this shared structure and recycling things. We can go into it more in depth later on. All right. So yeah, this is the thing like this. I mean, there is this family of map operations. Mapcar is basically like map. Okay. So I just wanted to show you this map thing, and there's this reduce. Think of it as it's a map. Okay, so there's a family of map operations. So mapcar, what it's doing is take you give a function, and you this thing you. So I can also do something like I can square. Okay, we had done this right. Xptx and then 2. So I can do this. Okay, and then I can reduce. Reduce is basically it gives you one value for the whole thing. This is the sum. All right, what is the final result that I want? I want the sum of all of them. Then I can say also star, right? So this is the summary of that. Once you get higher order functions, you should be able to play around with this. There's a lot of things here, and that's just the shared structure and recycling you need to take care of. Understood? Is it clear? So things become very simple once you get the basics right. So map list, and let's look at map list also. It's basically it's more just think of mapcar as more than enough. Okay, yeah, map list, what it does is, so map list, let me see how it works. It doesn't have an example. So yeah, the main thing is mapcar is more than enough. Okay, for understanding our, I mean, for our purposes, mapcar is more than enough. There's a series of this thing. Map list should be working like this. Let me just check this out. Let's just see what happens here. XPT123 is not a number. Okay. Okay. Takes it completely in. Yeah. So it actually gives you the complete list. It is doing this like this. So let's put it like this. Let's take it this way. Max x max. Okay, I think it's like maximum. Anyway, so it's basically giving a list actually, so we can look at that. It's much more thing. Mapcar is more than enough, because if I need anything else, we'll take it up like next class if you want to distinguish between this. So you can do a lot of stuff with just mapcar. All right, mapcar, what it does, it takes a function in, and it operates in each of those elements. Okay, to produce you one thing, and then you can do a map reduce, and you can do the compute the sum of some things. So reduce and then map. All right, so that's the means the short of this is something we had not covered last time. Okay, so anyhow, so coming back to that. All right, so let's go back to the macro that we are defining yesterday. So yeah, that's how you understand it. So what's happening here is it's actually computing the nth Fibonacci number. Okay, 0 0 starts with 0 0. Then current it starts with 0 0 n and current, so it becomes like 0, and this guy becomes 1. So you're taking the current next, you're summing up in the current, it will become next. Okay, what it was previously, it will just move here. Next will become current and next, current plus next. N is just tracking the it's just for tracking the variable. This actually computes the nth Fibonacci number by this current and next thing. You can see that it computes that. So this is the step form, by the way. This is the step form. It could be a symbol. So current becomes next, next becomes current plus next, like that. So 0, 0, 1, 1, and so on and so forth. Okay, we get the nth Fibonacci number in this do. Okay. So here we had this this thing. This actually does so do is quite important because you are writing that to this thing. So here you can also write it like this. This is also another do form. So it is quite I is 0 and greater than I 4. This is the end form. There's no result form. You can see that this is actually basically this. All right, and you can also return a result if you want by just placing this I here. So it will print and it will also return for you a result, and which you can then set fr into this result variable. Okay, which will be the last element that you had. So that's the general form of do. Okay, and you can see that do is quite complicated. So they also introduced something called loop. All right, loop there are two ways actually. One is the loop macro, which is just a general it loops forever. All right, so if you see this, for example, and the way you get out is by saying return. Okay, so let's have a look at this. Get uni plus universal time, let's say 120. Okay, so yeah, let's okay, get universal time, right? Is for getting the thing is this thing, and you can also set f that. I'll set it to like say plus that plus 150. So 1.5 minutes, 2.5 minutes, sorry. Okay, then I can run this thing. It will start waiting. It's going to sleep every 60 seconds. It's going to sleep. All right. So this is the loop. Basically, what happens is this is a when form, and you're returning in the when form. Okay, it is doing a check. It is checking if this is greater than some future date, which is basically I've set it as 1.5 minutes from 2.5 minutes from now. So at 2:25, 9:25 or so, it will be true. Okay, and then at that time it will return. Till then it will just say waiting, and it will sleep for 60, and it will do that. So that's a loop form. Loop form just keeps looping. Whenever if you want to come out of it, you have to do some check and you have to return. All right, that's the loop macro. And there's also an extended form, which is yeah, it simplifies things for you using collecting and so on. All right, so this is what this loop form does. Can you see this? So after 2.5 minutes it will actually it will come out of this thing. That is one thing. So let's have a look at this do form. So if you see the do form, it's a bit complicated, but it's more correct in the sense that you're setting up everything and doing it. You're creating an integer list called nums. All right, and you're setting I as 1 first initially. You have a step form, and greater than I 10 and reverse nums, and you're putting this in. So instead of doing that, you can do this simply in a loop form. So this is also a bit advanced. Okay, I'm just giving you a flavor of how it works. Like it's the same thing. Okay, but it does it simpler, and you can also have some very English type of constructs for doing this loop. So these are the extended forms. All right, we will not go much into it, but you can do all these things here. Okay, you can also do it. Yeah, you have summing and you have other things like this. So it's an alternate way of this is another way of, if you saw the Fibonacci thing, this is another way of doing it for Fibonacci. Yeah, this is another way of computing the n Fibonacci number. Instead of 10, if I had to put like 11, this would give me 66 or 89. Yeah, so yeah, so basically this is you'll have to pass through this, but we can do these type of things in loop. Loop makes it easier to do certain things. I mean, it's like some people like it, some people don't. All right. So, but there is something called loop for doing the loop construct, which is also a macro. All right.